something from what we have left the previous occasion.
Yeah, okay.
Yes, yes. So we will continue with the properties of continuous functions in this discussion.
I had solved some problems which you had already sent us, ma'am.
Okay.
Like the properties of continuous functions, addition of two continuous functions is a continuous function. All those algebraic properties I had tried showing using epsilon delta definition.
Okay. So I shall look into them,
Yeah.
and then tell you whether everything is fine. What is the token number?
Only 2, we have to wait for some time.
Oh, okay, then we can start our discussions here, right, till we get our coffee. Yeah, let's do it.
So you had to go to the post office yesterday.
Yeah, actually I finished that work. And you know what I discovered there? Some peculiarities there in the postal letter. Like if you have up to 50 gram, they will charge you 41 rupees. And just slightly above 50 gram, but below 100 gram, they will charge you some 71 rupees. Above 100 gram and below 150 gram, they will charge you some 101 rupees, and it goes on. Something, some good object.
Yeah. So this is like the price versus weight function. If we plot the graph of this function, then isn't it something similar to the step function?
Yeah, it's actually like that. Means there is a similarity with greatest integer function also, you can say.
Okay, so can you define the greatest integer function?
Yeah, ma'am, I can say. Yeah, that will be. Yeah. So greatest integer function is like for any real number. That's right. So the greatest integer function is defined by for any x in real number. I denote by greatest integer function by this symbol box x. It is defined by n when n is less equal x less than n plus 1 and n belongs to the set of all integer. Now for any real number x, we always know that real number always lie between two integers, that is n and n plus 1. For that integer n and n plus 1, I define the greatest integer function by x.
So in other words, you are saying that the integral part of a real number x is the greatest integer less than or equal to x.
Yes.
Okay. So why don't you plot the graph of this function?
So the graph of the greatest integer function will be like this. Then for any real number between 0 and 1, the value will be 0, and then in between 1 and 2 it will be 1, and between 2 and 3 it will be 2, and for the negative side between minus 1 and 0 all values will have the greatest integer function as minus 1, between minus 1 and minus 2 it will be minus 2, etc.
Yes. What are all the points where the integral part function is not continuous?
The integral part function is continuous everywhere except at the integers.
Oh yes, this is an example of a function on R having countably infinite points of discontinuity.
Are there real valued functions with uncountable number of points of discontinuity?
Yes. Let us take the function f defined by f of x is equal to x for x in Q, where Q is the set of rationals, and it is equal to 0 for x not in Q. What are the points where this function is continuous?
It is clear that the function is discontinuous everywhere.
Everywhere?
No, I think it must be continuous at 0.
Can you show that?
Yeah, I think I can show it.
Yes.
But how do you prove it?
Let me try. Let me draw its intuitive graph. So what will be its intuitive graph? It is something like this. On rational number, it is on this line, if x equal x.
Yeah.
On the irrational number, it is on this line.
Yeah.
So from this, it is clear that through rational or irrational whatever may, we are reaching to 0, our function is reaching 0. So let me try the argument by sequence criteria.
Yes.
So take a sequence xn that is converging to 0.
Okay.
So what I have to show? I have to show that f of xn goes to f of 0, and what is f of 0? 0, because 0 is a rational number, so f of x will be x in that case, and x is 0. So now let me calculate f of xn minus 0, that is mod of f of xn, because f of 0 is 0. Now since xn is going to 0, so for any epsilon positive, I must get a n naught, a natural number, such that xn minus x, that is 0 here, which will be mod of xn, it should be less than epsilon for all n greater or equal n naught.
Yes.
Okay. Now this inequality mod of f of xn, what it will be? It will be mod of xn when xn is in rational.
Correct.
Yes.
It will be 0 when xn is not rational. Anyway, that will be less than epsilon for all n greater or equal n naught,
Yes.
right? So whenever xn is a sequence going to 0, I get that for any epsilon there exists some n naught such that f of xn minus f of 0, which is 0, is less than epsilon. So this by sequential criteria gives f of xn converges to f of 0, which is 0.
Yeah.
So this shows that f is continuous at 0.
Yeah.
So that means it is a continuous function at 0.
Yeah, I was wrong. So, what about the continuity at the other places? Okay, let me show that it is not continuous at the other rational points. First, let me start with the rational points.
Okay.
Again, I will use the sequence criterion. Let x be a rational number and x not equal to 0.
Yes.
There exists a sequence yn which is completely in the set of irrational numbers such that yn converges to x. Now, f of yn is equal to 0 for all natural numbers n, because the function is defined as 0 on the set of irrational numbers. F of x will be equal to x because x is a rational number, and this x is not equal to 0. Now, we see that yn converges to x, but f of yn, which is the 0 sequence, does not converge to f of x because f of x is equal to x and that is non-zero. So, this by the sequence criterion shows that the function f is not continuous at any non-zero rational number.
Yes.
So, at all the rational points and x not equal to 0, this function is not continuous.
Yes, correct.
Yeah.
The same argument will hold for irrational number as well.
Yeah.
So let me write it. Means now you take x in irrational, in the set of irrational, then there must exist a sequence of rational Zn that should converge to x. Why? Because the set of rational also is dense in the real number. Now, what will be f of Zn? It should be Zn, and where it converges? It converges to x, but x is not equal 0, which is f of x. Why f of x is 0? Because x is irrational. So, Zn is converging to x, but f of Zn is not converging to f of x.
Yes.
That implies that f is discontinuous at all irrational points. that means what we are getting from collecting 1, 2, 3, we are getting that f is discontinuous on whole real number except 0.
Yes.
So, coming back to the function, you see that this function f defined by f of x is equal to x for x in rationals, and it is 0 for x not in rationals, is an example of a function having uncountable number of discontinuities. Right? Then what can you say about this function? Suppose I give you a function f of x is equal to 0 for x in q, and it is 1 for x not in q. Function is continuous. It is discontinuous everywhere. Exactly. So, here is another example of a function having uncountable number of discontinuities. Clear? Okay, that's fine. Okay, what about our coffee now? Is it ready?
I think it's only coupon number 6. Our coupon number is 13. We have to wait.
Discuss something useful till the coffee comes. Okay. So, you have started meddling with your mobile phone.
No, just checking the weather here.
So, is that the icon showing the weather?
Yes,
So,
ma'am, don't you think that this time the Chennai weather is so pleasant?
yeah, it is very pleasant. So, what does it show now?
It's showing 24 degree now.
So, taking the location of Chennai as a point on the surface of earth, which is almost spherical in shape, consider the diametrically opposite point. So, what is the probability that the temperature there is exactly the same as here at that instant of time?
No, Chennai is in upper hemisphere.
Okay.
And so the diametrically opposite point should be in the lower hemisphere.
Okay.
So I don't think they will have same temperature. So
Okay.
probably
I shall give another version of this question. Okay. Do you have a pair of diametrically opposite points on the Earth's surface which have exactly the same temperature at the same instant of time?
this must be tricky. This must be
Okay, I don't think it is tricky. Have you heard the intermediate value property?
Yeah, we have heard about it.
You have heard about this?
Yeah.
So, what does it say? See, continuous functions defined on intervals contained in R have very nice properties. And one such property is the intermediate value property. Intermediate value theorem states that if f from AB to R is a continuous function defined on the subinterval AB of R, and it takes values f of A and f of B at the end points of the interval A and B, then the function takes all values between f of A and f of B in that interval. That is what intermediate value theorem states. Is it clear? You have a continuous function f from AB to R. It is defined on a closed subinterval AB of R, and it takes values f of A and f of B at the end points A and B. Then the function takes all values between f of A and f of B in that interval. So, you see that this result is very evident for continuous functions for which we can draw a graph. So, if y equal to f of x is a continuous function and it takes values f of A here and f of B at the end points A and B,
Yes.
which is a sub interval of the real line,
Yes.
then the result says it takes every value between f of A and f of B
Yeah.
in the interval AB.
Yes.
So, the seemingly simple property has far reaching consequences. So, let me ask you this question: is there an irreducible cubic polynomial with real coefficients?
So means you are asking that whether there is a polynomial of degree 3
Yes,
which cannot be factored into polynomial of degree 1 and 2.
yes,
But we already know that every cubic polynomial with real coefficients has a real root.
Yeah.
And hence it will have a
It
linear
will have
factor.
a linear factor.
what is the proof?
Proof we don't know.
You do not know?
No.
Will intermediate value theorem help us here?
Yes, the proof can be given using intermediate value property.
Oh.
Okay? So, let us see. Suppose I take a cubic polynomial p of x with real coefficients given by a3x cubed plus a2x square plus a1x plus a0, where a0, a1, a2, a3 are real numbers.
Yes.
Then if I take a large alpha positive, then we see that p of alpha has the same sign as a3
Yeah.
Yeah, because x cube term will
dominate, and therefore p of alpha will be greater than 0 if a3 is greater than 0, and p of alpha will be less than 0 if a3 is less than 0.
Yeah.
And for large beta, which is negative, we see that p of beta has the opposite sign
Yes.
Of A3.
of a3.
Yeah.
So, we have p of alpha positive for alpha large, which is positive, and p of beta is one which has opposite sign as that of p of alpha.
Yes.
Or thus we see that p of alpha and p of beta are of opposite signs, and hence 0 will be between p of alpha and p of beta.
Yes.
Clear?
Yes.
So, and I know that p of x being a polynomial, it is a continuous function. So, I am justified in applying intermediate value property, and therefore, there exists a gamma such that gamma will lie between beta and alpha, and p of gamma is 0. So, what does it say? It says that a cubic polynomial with real coefficients has a real root.
Yeah.
So, now I would like to go back to
That
temperature problem.
Yeah.
Right. So, I pose the question once again. Right. What does it say? Do you have a pair of diametrically opposite points on the Earth's surface which have exactly the same temperature at the same instant of time?
So means since you are asking after this intermediate value property, we should use intermediate.
Yes, I have given a clue to you.
What should be the continuous function? Is there a continuous function on this Earth surface? Can we think of?
Okay, take a function defined by T of P equal to temperature at the point P.
Okay.
Is this function a continuous function of the points P on the Earth?
Yeah. points near P have temperature close to the temperature at P. So yes, this is a continuous function.
Okay, exactly. It's a continuous function.
Yeah.
And so now take a great circle through the point P. It passes through the diametrically opposite point P dashed.
Yes.
Now fix a point A on this great circle C.
Okay.
And define the function f from the great circle C to the set of real numbers by f of p is equal to t of p minus t of p dashed,
Okay.
where t of p is temperature at p.
Okay.
Now consider f at A.
Yes.
Now if f of A were 0, then A and A dashed have the same temperature and we are through.
Yes.
Otherwise, f of A is either positive
or
negative.
Yeah.
Now my claim is, if f of A is positive, then f of A dashed is negative.
Yes.
Do you agree with my claim?
Yes, ma'am.
How do you show this?
It is very easy.
Okay. See?
So, f of A is t of A minus t of A dash.
Yes.
Now suppose it is positive. Then what will be f of A prime? F of A prime will be t of A prime or A dash minus t of A double prime, but the diametrical opposite means it will be t of A, and it is nothing but negative of t of A minus t of A prime,
Yes.
which is less than 0.
Yes.
Yes.
So, if f of A is different from 0, then f of A and f of A prime have opposite signs.
Yeah.
So, that is what you have shown. Does that give you some clue?
Yeah.
Ah.
Okay, I think now I can complete the problem.
Right.
As P travels from A to A dash, f of P changes its sign. And hence, there exists a point P naught such that f of P naught is equal to 0. And this P naught lies between A and A prime. So, the temperature at P and the temperature at P dash will be equal. So, from this we see that because of the intermediate value property, we get that on any great circle there exists a pair of diametrically opposite points which have the same temperature at the same instant of time.
Yeah, it's a nice application and nice use of intermediate value property, right? Yeah. So now I think the coffee must be ready. Yeah. Token number 1, 3.
Yeah, 13 is ours. Finally, our coffee is ready.
Yeah. Let's have coffee. Thank you.
Thanks.
Thank you. Oh, ma'am, be careful.
Oh.
The table is slightly wobbling.
Oh.
Even though the 4 legs of the table are of equal length, it's the uneven ground that is causing the wobbling of the table.
Oh. You want me to solve this by intermediate value theorem?
Ma'am, are you joking?
No, I am not joking. Intermediate value property has a remarkable solution for this.
Really?
Yeah.
What will be that solution?
No, I don't want to give the solution. I leave it for you to think about it. We have discussed enough of intermediate value property and its application. So, I leave that for you to think, right? So, let's have coffee and go to our work.
Yeah, okay.
You think about it and come back later, right? So, come with a solution.
Yeah.